As we talked about in the previous video, we can completely define the mathematical behavior of a first-order system if we know the initial condition, the final condition or the final steady-state value of the system, and the time constant of the system. Now, we've also established that the time constant depends upon the system being analyzed and that the time constant has to be determined based on the differential equation. The time constant is the value of the coefficients that are in front of the first order derivative term when there are no coefficients in front of the zeroth order or the non-derivative term of the differential equation. The time constant is a defining characteristic of the first order system, and it measures, or it's a measurement of how long it takes the system to reach steady state after a disturbance. Because it is the time constant, it has dimensions of time associated with it. All right, that is, it has units of seconds. So a time constant here tells us the time to reach steady state. And we'll have to define what steady state is in just a minute here. But we know that the free response of a first-order system is given, or the homogeneous response of a first-order system is given by this general equation right here. We have some initial condition and then an exponential decay back down to 0. Okay? So if we substitute different values of time into this solution right here, let's take the first case where let's say that the time is going to be tau. All right, so one time constant. After one time constant, we're going to have the initial condition multiplied by e to the negative 1. All right, and when we evaluate e to the negative 1, we get 0.368. So what this tells us is that after one time constant has passed, the free response of the system has decreased to 36.8% of its original value, its original initial condition. Okay, and we can repeat that again. We can say after two time constants have passed, the system, the free response has decreased to 13.5% of its original value. If we wait 3 time constants, then it's decreased to about 5%, a little less than 5% of the initial value. If we wait for 4 time constants of time to pass, we'll be evaluating e to the negative 4th, which is about 1.8% of the original value. And after 5 time constants have passed, this exponential term is evaluated e to the negative 5th power. We're less than 7%, we're less than 1%, we're at 0.67% of the initial steady state value. So after 5 time constants have passed, we're less than 1% away from the steady state condition of the system. We're almost back down to 0. So for the purposes of this class, and most of the time in systems analysis, we consider steady state to be reached after 5 time constants have passed. So that means that after the system has decreased or has changed from its initial value, and it's almost all the way to its final steady state value, and where that differs by e to the negative 5th, that is when the system has reached steady state. So again, 5 time constants in this class is what we're going to consider to be steady state condition. Now you'll see in other fields, sometimes they'll consider steady state to be close enough to be 5% away. And other times you may see larger values of steady state definition. But it takes 5 time constants for steady state to be reached by most definitions. Okay, and again, one time constant is the time that it takes for the free response of the system to decrease by 36.8% of its original value. All right, so let's look at that graphically and what that means. So the time constant is the time that's required for the system response to reach 63.2% of the difference between the final and the initial value. Alright, so here we have a system that doesn't start at 0 and it ends at some non-zero value. So what we're looking for here is the amount of time that it takes for the system to go, the difference between the initial value and the final value is 8. So we're looking for the time that it takes for the system to go from 2 up to 63.2% of this difference, which is 8. Alright, so we're looking for the time constant. The first time constant will be somewhere around here. Alright, because that's the time that it gets about 63% of the way up from its initial value to its final value. Okay, and the reason that we've come up with this 63.2% is because that is 1 minus e to the negative 1. So that's the difference between 1 and e raised to the negative 1. So this 0.368. Okay, so that is defined as one time constant, and 5 time constants later, the system has almost equilibrated at its final value. Of course, because there's this exponential function that defines how this system response goes from the initial value to the final value, we know that it's going to asymptotically approach this final value and never fully reach the final value. But we consider that after 5 time constants have passed, it's close enough. It's less than 1% away from the final value, and we say that the system is in steady state at that time.